Dr. Hanks, you're muted.
All right, thank you. Hello, everybody. Today is Monday, September 18th, 2023. I'll be recording to the cloud today to record this lecture. Last week, we had a lot of fun. We worked at learning the anatomy of a neural net. We talked about forward propagation, back propagation, and a lot of the code examples that we started going over Wednesday were in this week's module. What's new is this notebook called How Are Neural Nets Nonlinear? And then there's a video on how activation functions add nonlinear to neural networks. There's one on how to set up the TensorBoard video, and your homework assignment due September 25th, a week from now, is going to be using the TensorBoard. And we will work on that as a working session in class on Wednesday. So we'll load that up and get started. You may, and I highly encourage you to download this code right here, which we will modify. It's called Chapter 2, Chalet 1 walkthrough. We will modify that to add TensorBoard to it. Today, I'll be going through slides for this week, starting with some feature engineering, embedding, and regularization. And then there's an optional code down here. I'll show you guys this today. It's just the next, it's an Excel worksheet that takes you step by step through how to do back propagation. So that's kind of cool. And then just to round this out for next week, you may have already completed a lot of the things for this week. A little bit ahead in the content, which is fine. We're going to sync up here soon. Well, I'll give an update on project 1. I'll do an introduction, and then we'll have a couple of working sessions in class, so you'll have time to work on that and ask for feedback and questions. Okay, so let's take a brief look at week 6. And you can see here, we're continuing to talk about overfitting, and then this new concept I'll introduce today, regularization, and then dropout regularization, and a lot of the things, examples and extensions of what we've already learned. Okay, so that's the direction that we're going. Get everybody on the same page, and let's kind of dig into some slides for today. So the topics for today are going to be primarily feature engineering, embedding, and regularization. Some intro on these new topics. Okay. Some data considerations. We learned last week through our assignment that the training data and the test data need to be of the same, I called it ilk, same type. Realize that if you acquire data with Microsoft Paint, and that's different than the way you acquired your training data. If you acquired your test data with MS Paint, what we did, and acquired your training data through a camera and imaging, that creates a challenge in the training. So both the training data and the test data need to be of the same ilk or type. And then be careful that you're not having the same sample in your training and validation set, or in your test set for that matter. So we're kind of building up a checklist here. So what we've done for pre-processing, we've done vectorization. All inputs and targets must be tensor floating point data. We converted text, for example, for the Reuters data into floating point vectors. We implemented normalization or standardization if you're dividing by the standard deviation, and we came up with methods to handle missing values. We can remove the samples or observations with missing data. We can use a 0. We need the same, whatever process we use, by the way, for removing the data. If we apply a 0 or we apply a mean in the training data, we need to do the same thing in the test data. All right, so we're going to make sure we do everything exactly the same that we do in the training data as we do in our test data. Okay, that's kind of cool. All right, this concept of feature engineering will be more important and maybe very important for your project 2. And that the idea is, how can we abstract information out of an image or your data set to make it simpler to train, less, and use less computing power. And a simple example is, if I have a watch here or a clock, and I have images, and this was a large image of data, we pass all this data in. If this was 1,000 by 1,000, it'd be 1,000,000 samples per image. Another option is to come up with what the angle is between the hands on the clock. And that could be just a few data points. The angle and the location of one of these points would just reduce the data down tremendously. So we wouldn't have to store off thousands of images for our machine learning example with every time and every minute, every hour and every minute. We could just, record a few data points within the image. So for the image, abstract the features into a new data set. And that's the idea for feature engineering, okay? So feature engineering is key for resources. I have a little example that I've created. Maybe it's a little too simplistic, but that's always good. Here's a feature example to show you guys what I do on the weekends. Here's what I do with my free time. Is I came up with a model to predict NFL teams that were going to win. So this is from the 2019 season. Here's the win percentage, and I have these features. This first feature is offensive yards, OY, minus defensive yards against. Okay, so it's column E versus column F. So that is, in a way, I did some feature engineering here, and then I used the statistic called takeaways, overall takeaways. So takeaways. So Baltimore had 13 turnovers, net turnovers. So they got the fumble interception 13 more times in the competition. So they subtracted the takeovers the fumbles that they had versus the ones that they gained. So that was another feature abstraction, offensive yards. So I came up with this model that does a prediction. It's a very simple linear fit. It's pretty good. Our squared value using the net turnover rate versus plus the offensive yards minus the defensive yards. So defensive yards, by the way, that's an independent feature. That's kind of cool. Is how good is my defense and how good is my offense? It's real clear that those are independent features. They're not really related to each other. The thing that turned out interesting to me is that the penalty yards really didn't matter that much. Here's, I've got the correlation with the win percentage down here. It's a negative 31%. The opponents, if they have less, this makes sense. If they have fewer penalty yards, they're more likely to win. Slight correlation with penalty yards for the team that wins. So that's probably close to zero. We don't have that many samples. So an example, maybe a very simple example of some feature extraction for predicting NFL win games, okay? All right, so I'm going to introduce a new kind of feature engineering feature here, especially for text data, and it's called embedding. All right, I believe that you can see my slides now. Is that true? Give me a thumbs up, please. Having troubles with my Chrome today. All right, thank you, Ainsley. All right, so we're going to talk about something called embedding. Embedding is a way to map high dimensional data into a lower dimensional data. So if you remember, when we did one-hot encoding, we took 4 different inputs and we categorized them into 4 different columns. And so that created a new array. Instead of having this ranked from 0, 1, 2, 3, we said, we need to one-hot encode this because there's no ordinal information in this categorical data set. So we went on hot encoded it, but it created this huge array. And especially for word applications where you're encoding word information or language information, is if we have 1,000 words and each of them are different, we end up with a huge array, 1,000 by 1,000. So how do we minimize dimensions and vectors so we don't use up memory space? The reason I was having my Chrome was crashing is that I ran an example where I took all of the words in the movie reviews and I hot encoded them, which created this 1 terabyte memory problem and crashed my computer. So you don't want to do that. But if you take the words and you create vectors out of them, this is kind of interesting, is it allows you to reduce the dimensionality and you can get semantic information out of the words themselves. For example, so we've got gender on the x-axis and age on the y-axis. So boy, man, and grandfather, same gender, yet the age is different, right? So for the word boy, similar or close to, have semantic information related to man and grandfather. When woman and girl, different gender, and then in the middle here is adult, child, and infant. So this is an idea of how you could create a vector. X of 1, Y of 2 equals boy, X of 5, Y of 7 equals adult. And then also, because of the vectors here along the x-axis, we have the gender, there is semantic information. So there's semantic power in embedding these terms. And there are algorithms, programs out there that will embed the words for us, and we can include that in the model. All right, so high level here, the takeaway is there's semantic similarity in embedding words, and words with similar meanings are closer in the embedded space. Analogical analogy relationships, embedding can capture relationships like man is to woman as king is to queen. This ability to capture the semantic relationships makes embedding extremely useful for NLP, natural language processing. That's what NLP is. And when we type into ChatGPT, it's actually using natural language processing, or we speak into Google using the audio terms. It's actually using NLP to convert that into meaning and entities and then do the test results. So why use word embedding? An example I'm about to show you, we went from 10,000 by 10,000 into dimensions, 10,000 dimensions into 32 dimensions, dramatically reducing the amount of memory that's being used by the compute engine. Feature learning, embedding can be learned from the data itself, allowing the model to focus on the most important aspects of the data. So embedding is a type of feature engineering. Generalization, a good embedding space can generalize well to unseen data. So in a way, we're creating a model for doing embedding, and then we're going to use that model in our machine learning model. And this embedded model can be generalized for new data samples. And then interpretability. Lower dimension spaces can be more interpretable. 2 or 3 dimensions humans can think in, but 1,000, 10,000 dimensions, very hard to visualize and grasp. All right, let me show you a couple of examples of this. And then the last thing here is efficiency. We've already talked about this. Lower dimensionality makes computations more efficient. And then introducing this idea of transfer learning. We can do pre-trained embedding models can be used in our machine learning model. And then overall it improves performance. Okay. All right, so that's the concept of embedding. If you remember back to our applications, we used, let's see, where is that? One hot encoding. And what I've done here is I've loaded in the movie review data. And if you remember, the movie review data had a lot of samples, had thousands of words, and then we said we want to take the top, we're going to take in this application the top 1,000 words, and then make the maximum length of the reviews 100. Well, we may take the 1,000 top 1,000 words, but if you think about it, if we take a review, not all 1,000 of those words are going to be in the review. And then once we map all of those, the word frequencies to what's in the review, we want to take the top 100 words. So that's what all this is doing. And then I made a note to myself there, one hot encoding creates a memory error. So if we run this code and we one hot encode everything, this is the error that I get. It says, oh, there's a 9.3 gigabyte array that you're trying to implement here. And by the way, once you get this memory array problem, future applications, you got to stop the kernel and restart it. So I don't want to run that code right now. So that is just to show that you get an error because we have such a large application. So now what I'm going to do is I'm going to build a sequential model like we've been building, but use this new feature called embedding to be able to take the multi-thousand dimension array, and actually it's going to make an array of 32. I probably should have just called that 32 dimension equal 32. So it's a vector that has 32 dimensions as opposed to 10,000 dimensions. And if we run this, it actually converges really quick here. We get an accuracy of 77% for our reviews. And then I went on and I added in some regularization, which we're going to talk about next. Okay, so I'm going to wait and show that. I think it's easier to show the regularization over on a different data set. So let me do that. I'm going to come over here. This is the MNIST handwriting data that we've been working with. And I did a couple of things here to see if I could force the data to be overfit. So I only trained, remember that the MNIST data set has 70,000 images, and I only trained on the first 2,000. Right, so that's what I did there. And then I came up with a model called no-reg. So we're not going to use regularization in this model, but I have a pretty dense neural network here with one layer of 512, another layer of 512. And I'm only training on the first 2,000, but then realized that there's 70,000 observations here. So we could overfit on the first 2,000 and then try to test it on the rest of the data and see the overfit in our evaluations. Okay. So that's what I did in the first model. And then I created a second model. And here I'm going to introduce some new concepts for us. By the way, I used the Atom optimizer. We talked about that last week and I used the sparse categorical cross entropy loss because we really are doing a multi-class categorization here. We got 10 classes. So in this model, I'm going to call it model no regression fit. Notice that that was the one up above, and the one that we're going to run next is called the model with regularization. And here I've added in this parameter to this dense method. I'm going to use the same number of neurons in each layer, 512, 512. Activation is going to be ReLU, and then I've added in this keyword parameter called kernel regularizer, and it says L2. Now that's a little confusing that it looks like 12, but that is L2, and there's also an L1, and we'll talk about that in just a second. Then I added in what's called the lambda, and let me show how this works, and then we'll talk about the math that actually implements this. So we created this new model, and we've added in this regularizer, and then we run the model with the same optimizer and loss and metrics. Now notice here, I ran 50 epochs, a lot of epochs this time, and did a validation split of 0.2, but I only ran the data on the training, a small subset of the training images, the training data set, which was 2,000 samples. All right, I don't want to run through all this for you. It took a while to run through, so run all this, but what I did is I plotted the results. Here's my plotting code. And then I plotted the validation accuracy here. And notice that the accuracy for the regularization kind of went up, and then it shot back down here around 30 epochs, and then it went back up again and performed better than the validation accuracy with no regularization. Does anybody have a guess of what's happening there? Just write it into the chat. I'll let you think about that for a second. Why did the orange line drop down and our accuracy went down and our loss went way up right here? About epoch 28 or 29. Anybody have a theory on that? Come on now, help me out. Put something in the chat. Oh, man, that was a perfect answer. It hit the local minima in the cost function. Yeah, when you see the overfitting, go try to reset the weights. I think that's a good guess too. The steps were too big. I like all of those. Nice job, everybody. Cool. So what I believe happened is it had found a local minima, but now we're adding what's called a penalty to the cost function. We're adding a penalty to the cost function, so it jumped off of that local minima and went to another minima, and maybe could even be a worse off solution than up here, but it went to what we hope to be the global minima. All right, so it got knocked off one minima and went to another minima. Okay, so that's kind of cool. So let's go back to the slides here and kind of talk about that in slide form. Okay, there's many types of embedding, kind of jumping around back to embeddings, which is feature engineering. And really what we want to do is use feature engineering to minimize our resources, but then also we want to use regularization to address overfitting. So regularization is the process by which we can address overfitting. That's kind of a key message here. And we could do some simple things, like we could reduce the hidden layers, the number of hidden layers, and the neurons in hidden layers, and create a real simple model. And that would reduce overfitting. However, you guys may remember we talked about the model being biased and or a model having high variance. That would make the model have high bias if we made it too simple to actually recognize all the features. So we're looking for this balance once again. So this idea of regularization is to constrain the complexity of the model and to make it somewhat simpler and more generalizable. So we're going to use regularization. So how does regularization work? Well, we add a penalty term to the loss function, discouraging large weights. So if you get a large weight, we're really locking in on one feature, get a really large weight, then by adding a penalty that is a function of the weights, then we will bump ourselves off of that large weight. Types of regularization, there's L1 regularization. It encourages weights to be exactly zero, effectively removing irrelevant features. So you can have irrelevant features, samples in your input data, and a good model that's generalizable won't use those irrelevant features. That's kind of cool. Just throw a bunch of data at it, even if it's irrelevant data, the model will learn data. So I get asked that question sometimes. Well, what if I add in this data and it's really not relevant? Does it affect the model? It can if it has a lot of noise and the data starts training to it, but this regularization techniques really prevents your model from picking up irrelevant information. Okay. And then L2 regularization encourages weights to be small, but not exactly zero, leading to a more balanced model. Okay, so let's look at the math. And I'll work through the math on the cost function, and I will work through the math. I have a video that works through the math on L2 regularization, and that's your next assignment, actually, after the one that we finish on the 25th. So with L1 regularization, so remember that we call the cost function or the objective function or the loss function, those are all the same meaning, J, and then J is a function of W, that's our original loss. And what we do with L1 is just the weighted absolute value of the weighted of the weights times a lambda, which is a factor. Okay, so that's a hyperparameter that you set. Okay, and then L2 is the weights squared summed up times some factor, okay, the lambda. So very simple, and you can think of this as a penalty, right? Oh, we're trying to minimize the error, and then we're adding something into the error. Oh, that doesn't seem so intuitive, but it's a function of the weights. Like, so if you have a really large weight here, then you will throw this off and adds in a penalty. But if all the weights are becoming smaller and are equally distributed, then you have less of an issue. Okay, so that's how to read that. Okay, and then I'll show a couple examples here. This is from chapter 4 of Deep Learning with Python, Cholet. So here's an example that shows using the model by reducing the complexity. I'm going to go to 2 hidden layers with 4 neurons right here. Okay, that's what this says. Whoops. And that's what this says right here. All right, I've got 2 layers, 1, 2. I've got input of 10,000 is my sequential model. So this is a vector of 10,000 samples long or observation long, and I have 4 here, and then up here I have 16. So the original model validation loss is increasing, and this one has less overfitting here. Okay, so it's an example of simplifying the model. Now, if I have a more complex model with a lot of neurons, you can see that how the effect on both the validation loss for the original and bigger model and the effect of the model capacity on the training loss. Okay. The example that if we add regularization, you can see that the regularization kind of flattens out here for the L2 model. Okay, so regularization to mitigate overfitting constraints are put on the complexity of the network, which makes the distribution of the weights more regular, and that's why it's called regularization or weight regularization. There's a cost associated with having large weights is added to the network. And then L1 is proportional to the absolute value of the weights. L1 is absolute value of the weights, where L2 is proportional to the square of the weights. L2 is square. Okay. And then here is the syntax. Kernel regularizer, and then I can select from the regularizers. This is actually L, not 1, L2. And then this is the lambda right here. What's the lambda value here? All right. Okay. There's another type of regularization called dropout. And dropout works by adding zeros to makes the output features from one layer to be 0. So this guy here is a 0. If you picture this as a weight from from, not awake, but the output of a single neuron. And then, let's see, the next one here would be, let's see, this one right here, these two right here were set to 0. So what does that do? Oh, how does taking an output from one of the hidden layers, neurons of the hidden layer, so these are each of the neurons for the hidden layer. We apply dropout, we basically turn those into 0. So that goes to 0, those two go to 0. This one went to 0. So that's kind of interesting because basically you can interpret it this way, is that the units, the neurons that conspire to collaborate to find a local minima, if you shake it up, if you change the weights, then a new minima is found. Oh, that's kind of cool. It's like we shake it up and say, if you start from a different point doing gradient descent, and then another deep minimum is found. Okay, and here's how we add this capability in. It's pretty simple. It's just a layer that called a dropout layer right here. You can use ChatGPT on all of these and say, how do I add a dropout layer to my model, and then generate the code for you. Okay. So notice we could even add that after we do an L2. So you can use both together. You can use L1, L2, and dropout all in one model. The model that I just showed you here is, I believe, the dropout and the L2 regularization kicked us off one local minimum, and then we started training to another local minimum here. The validation loss shot up, and then ultimately looks like it was even going to maybe converge even lower down here at some point. But we did 50 epochs. So another takeaway is that when you add regularization, it typically takes more epochs to come to a converged accuracy. Okay. We were getting an average about here for accuracy, and then we're now about here. So maybe this was even a different. We probably needed to give it a few more iterations to get to that new local minimum. Okay. All right. So we're developing kind of a workflow for machine learning. We've kind of gone through this a little bit, but we're adding to our workflow. Your data should be sufficient to learn the relationship between the inputs and the outputs. That's real key. You got to have enough data. So this one's key right here. We have to identify the top problem that we have. Is it binary and multi-class? Logistics problem? Is it a regression problem? Remember, we can use machine learning to do regression. We've been mostly focusing on these classifications, but you can use it to do regression. You just don't have a soft max output. That's that, pretty much that forward. Hypothesis 2 is your outputs can be predicted given the inputs. Okay, understood that. We have not talked about non-stationary problems. I'll do that later. People about this time in the class start saying, well, let's predict the stock market. And the stock market is non-stationary, meaning that the input observations today in year 2023 do not match the historic input observations or parameters that affected the stock market. So the input data and the features are changing all the time. It's not like a chemistry or a physics problem where nature always repeats itself. Human psychology does not repeat itself. So very hard to use machine learning to predict the stock market. So that's kind of a takeaway from non-stationary. You need to identify, is your problem, is it non-stationary or is it stationary? Okay, so that's kind of interesting. And then, and you will use this checklist pretty much for your project 1 and project 2. So it's a good thing to know. What's your measure of success? Accuracy usually, but maybe something related to customer retention rate, business goal. What's your evaluation protocol? We've been primarily using holdout validation. We've talked about k-fold validation, but we have not programmed it yet. But pretty simple to program, but that's, we talked about k-fold. We got to format the data into floating point tensors. We have to normalize. Now we need to do feature engineering, especially on small data sets. Some kind of human logic for feature engineering often is required for very small data sets. If it's a large data set, we can rely on the neural net to find an answer. Feature engineering, though, if the data becomes so large and we can't do the processing for the compute engines that we have, we might need to use feature engineering to reduce the computational load. Okay. I always like to think about what is the baseline. Okay, the baseline basically for MNIST, since we have 0 to 9 and it's a balanced data set, balanced meaning there's the same number of observations of ones as there are nines and so forth, is that if we have 10 classes, then we ought to get about a 10% probability. We just randomly guess we'd be right 10% of the time. So that's the baseline model. We got to be better than 10% in our model to say that our model is effective. Right? Then define the hyperparameters. Okay, we're going to use all these different, what type of activation we're going to use, what's the type of loss function, what's the optimizer configuration, what's the learning rate. And then, this is interesting, develop a model that overfits by adding layers and making the model kind of very complex, and then back off and try to make it simpler and see if you can get just as good at accuracy and minimize your overfitting. Oh, that's kind of cool. It's like we want to really overfit it, and then we want to add regularization, dropout, simplify the model, and see if we can get just as good at performance. Okay, so that's a pretty good little outline of where we're at right now. Okay, I did want to point out to you guys a couple of other things. The last layer options. We're going to cover these in the reading in chapter 4, but we've been talking about primarily multi-class types of observations. We've been talking about binary and multi-class observations. We've been using the softmax output as the last layer. We've been using these loss functions. Okay, those are all good. Same thing for multi-class, multi-labeled classification. And then regression, we should use mean squared error. And then regression between 0 and 1 is a sigmoid, because sigmoid squishes everything into 0 to 1. So depending on the type of problem you have, you need to pick the last layer activation. We've been making it simple so far and have primarily used softmax. Okay. And softmax gives you a probability in multiple classes like we've been using. It gives you probability for each of the classes, and then you choose the class that has the highest probability. I tend to kind of like to do that. That way I don't have to think about this last layer that much. I just use softmax and then choose the highest probability solution. Okay, the final thing I wanted to show today, I got another set of code that shows you that there's a lot of data, a lot of different examples over in the MNIST data set. Here's another data set. This is called the fashion data set. You can think of this like a web page, and they have all of these samples of products, and they want to categorize the products into different classes, so we have 10, 1, 2, 3, 4, 5. We have 10 different categories or classes. T-shirt, trouser, coat, ankle boot, so forth. Here's what they look like. Once again, they're 28 by 28 images. So this is an ankle boot. I wouldn't call that a high sandal, but that's what they label it as. It's kind of a high heel. Okay, so here's a t-shirt. There's trousers, ankle boot, so forth. Coat. There's one down here called a coat. I think that would be hard to tell the difference between a long sleeve shirt and a coat. So what I've done here is I've added in dropout and L1 and L2 to show how this works. Now we have these regularizers and these other layers. And we went through our checklist, normalized data, flattened it out. This is the same thing as multiplying 28 by 28 and taking the input shape to 784. The 512 first layer, softmax, 10 outputs. And then we can go through validation and accuracy here. And we get really good accuracy through our training, about 90%. And then I made a little bit more complex application and use 512, 64, 32, 16, use dropout, use regularization, and plotted the results of that, or ran the results of that, and then plotted the results. So ultimately, what I'm going to ask you to do for project 1 and project 2 is to do something similar to this. Compare and contrast a couple of different models. Okay, so that's what we're leading up to do, using all these techniques that we've learned up to that point. Okay, I'll stop here and see if there's any questions about the new content that we've covered today. Thank you for your participation and attention. And if you don't have a question, feel free to drop off. I'll see you guys on Wednesday, and we'll do a little working session in class. I'll hang out, see if there's a question.
Should be good. Thank you.
All right. Thank you, guys. Have a good Monday evening, maybe a little Monday night football.